Welcome back, chemists, to my third video on galvanic cells. In this video, I will model again a particulate view of what's happening as the cell runs, the galvanic cell operates. We will start to see that we are leaving standard states and the voltage will change, and in my fourth video I will calculate how it changes using the Nernst equation. But in this video, the calculation that we're going to do is if we are still at standard conditions, we can calculate the Gibbs free energy change for this process or for this galvanic cell that we are operating at this point. All right, so let's get started with the modeling first. All right, so let's start with our zinc half cell. Remember in the first video, we started with 6 zinc atoms. And what I'm going to do is I went back and forth, but let's have 2 more zinc atoms leave. Okay, so what that means is I'm left with kind of 2 in my little model. I'm just going to dot these out for a second. Don't add these. I wouldn't add these unless you know that. I mean like they're gone. Okay, so what happened is these 4 are now in the solution. Take a look at that half reaction. Okay, and we started with 6 for the first video when we made our zinc sulfate in 1 molar solution. Then we added 2 more in our second video. And now I have 2 more that I'm saying have been added now since this cell has been operating. All right, so let's add in our sulfates because this is actually a zinc sulfate solution. I'm going to kind of zoom into the zinc sulfate portion. Remember in the first video we had sulfates being added immediately and that they were really tetrahedral polyatomic ions, SO4 2-, but I just did a red dot. Okay, then we added 2 more from the fact that we had 2 zinc turning into 2 zinc ions. And now I just had 2 more do that. So that means again in the salt bridge, I will have to send in some more sulfate to balance that charge. So I'm going to say kind of the same thing as the last video, 2 more sulfate will have to enter. And then the whole point of this is to generate these electrons that are going to go up through this wire. You know, they're going to leave the zinc, go up through the wire, and then go through the voltmeter and be measured, come through, and kind of make a complete circuit here and come through here, all right, into the other half cell, which we'll talk about in just a second. Now again, if you want to say that we had 2 zinc, then we'd actually have 4 electrons. If you feel like that, you know, helps you make sense of it, great, okay? And these electrons are traveling through the wire in that direction. Now, we are going to see that we are not really at 1 molar anymore, and the voltage, or the voltmeter, should start to read a little less, if it's a sensitive voltmeter, a little less than 1.1 volts at some point while this is operating. And then in the fourth video, we'll talk about what happens when, you know, you're really far from standard states. Okay, but let's keep going with just saying we're starting to, you know, leave standard states behind. Let's go to the other side and talk about what's happening with the copper. Okay, so to make sure you take a look at that half reaction. Remember in the first video, we had 6 of these copper atoms to start. Okay, that's just kind of how we started before we added even the salt bridge. In the second video, we had 2 more being turned into copper atoms. And then in this video, I'm just saying again, let's just go 2 more and say it's pretty close to operating at standard conditions. So if we had 6 at the start, copper ions, we only have 2 left. Now think about again what's happening with the molarity, because I'm going to go to that next. But we had our 6 sulfates at the beginning. They're still in there, you know, they're not going to go anywhere. They're in solution, attracted to the water molecules. I'm not even drawing. And I hope you remember that what we did to balance the charge is we added some sodium ions, and we had to add 4 to be able to balance the charge. But now I have 2 more missing, so through the salt bridge, I have to send in, you know, or not me, but there has to be sodium ions that are sent in or attracted in there to balance that charge, to keep the neutrality. I always say like I'm in charge of it. I'm not. Okay. The other thing, let's do some coloring of that copper 2 sulfate solution. It would be even a little less blue. So however you want to color this in, make sure it looks a little bit lighter. It's hard to do that on the iPad. All right. So let's write some stuff about this solution. Okay. So let's stick with the copper. If you take a look, if I only have 2, you know, on average, or 2 left in that area, my copper 2 sulfate molarity is decreasing. So copper 2 sulfate molarity will decrease. And you can have it as a visual image right above you. Of course it's decreasing. I have less copper ions in there. Plus you'd see the color changing to be less blue. So I'm going to do is just do a little arrow and say my 1.0 molar copper 2 sulfate solution is really kind of starting to not be 1 molar anymore, if you want to add an AQ. All right, what about the other side? Let's talk about that zinc then. So take a look again at your zinc sulfate solution. So the zinc sulfate solution molarity will increase. And you can really tell if you look at this picture, flip back. That's why I have this as a flip book. Or look back, if you made a digital version, look back, and you can obviously see there is a higher concentration of zinc and sulfate in there. So I'm just going to draw a cute little arrow up that says my, 1 molar, my standard conditions are starting to not be standard because I'm leaving, the solutions being 1 molar. They're actually being higher or lower. All right, last but not least, before we move on to the delta G calculation, let's talk about these electrodes too. So our zinc electrode mass will decrease, and you could even add like a decrease more than the last time. That's why these images are kind of nice that you don't have to, get them. You go to the YouTube description below and boom, you've got these for yourself to use. And the copper electrode, so you don't have to draw all of that. Copper electrode mass, kind of not the best sentence, but that's okay, will increase more because we're having more and more of those copper atoms being plated on the outside there. All right, so I'm just going to take one last little look and make sure I have everything that I wanted to talk about with the particulate model and kind of proving why we are kind of leaving our standard states at this point. And I think we're good. So I think we're good to move on to the delta G. So if you go back, to the section that's above this, you can write down the equation. And I already wrote in that delta G is the change in free energy at standard conditions, or Gibbs free energy. So let's go over everything else that's in this equation, and then we'll calculate it for our little galvanic cell we have here. So this is the moles of electrons transferred in your reaction. So this number is going to change. It's not a set number. I'm just going to make it a little zoomed in here for us, for our copper reaction that we're doing. It's gaining 2 electrons from the zinc and turning into copper 0. And if you want to write both, your zinc is giving off the electrons and turning into ions. So again, we kind of had a nice one where the electrons are the same. So our electron, our N, in this case is going to be 2, okay? What is F? Well, F stands for Faraday's constant. So this is a constant. And you'd always be given this constant. You do not have to memorize it, at least I would hope not. And it's 96,485 coulombs. I'm not going to talk about what that is in this video, but it's coulombs per mole of electrons. So the per mole. Now, if you don't want to have the per mole like that, then you're going to have to put that in the denominator like this, per mole, or you could say per 1 mole even, if you want to add the 1 mole of electron. All right, whatever version you like. I hope you kind of know what E cell is. It's the cell potential at standard states. And then the other thing that we could use is you can use this delta G equation for anything that has what's called electromotive force, but really for most in chemistry, we use it a lot for galvanic cells. So that's why I kind of have 2 versions up here that you could use for our Nernst equation. All right, so let's just get started with some two facts before we even do the calculation. So if your E cell, and you can see if you want to write your E like that, or I kind of write it sometimes like this. I kind of vacillate back and forth, but today I'm kind of feeling this one. So my E cell, just because some books will look different, is greater than 0, and that's kind of what we wanted. Remember, we took the zinc half reaction and we made it an oxidation, and we did that because we wanted the process to be favorable. So in this galvanic cell specifically, so process is favorable, or spontaneous if you like that word, but most people are switching over to favorable. And the delta G is negative. And that's kind of what it means to be favorable, is if your delta G is negative. Alrighty. Now, what would the opposite be? Okay, well, if our E cell, and you could have a problem like this. You could easily have a problem where the voltage ends up being negative. And what that means then, they're kind of testing you, is do you know that then that process is not, for the direction it's written, it's not favorable or spontaneous. And what will happen is then the delta G is actually positive. All right, so you can kind of tie in some thermodynamics here with electrochemistry. Very common. All right, so now let's calculate our delta G for our, our galvanic cell that we've been using. All right, so I'm just going to kind of show enough of this equation right here. So we're going to calculate the delta G at standard conditions, and it's the negative number of moles of electrons. So we had 2 moles of electrons. And then use Faraday's constant, which is 96,485 coulombs. And I'm just going to put per mole like this because it lines up nice, and you can put the little mole of electron there. And then 1.10 volts. Now, if you have gone through thermodynamics, you should be saying, wait. Usually we have this in kilojoules or joules as the unit. And if you're a person in AP Chem or Chem, by this point, you should be saying the units don't look right. Okay, so you need a cute little fact that I call a cute little fact. You need this fact that a volt is a joule per coulomb. So what I'm going to do is just kind of rewrite this again and just kind of do a couple things with the units. I'm just going to say -2. I'm going to get rid of the mole of electron and say that that canceled with this one. And then I'm going to say I still have the Faraday's constant, or the number. And then I'm going to change this to be 1.10 volts. And then I prefer to put coulomb to the -1. But if you want to write it in the denominator, you can. It just lines up nice this way. So then that'll cancel. Oh, not a volt. My mistake. Sorry about that. Hopefully you haven't erased it. I meant joule. Sorry. This whole point was to switch it to joules. Maybe you were thinking, wait, that's not right. Good catch. Wish you could have told me out loud, but it's a video, so you can't. Okay, moving on. So it's joule per coulomb. So you might have been wondering, whoops, I made a mistake. Yeah, we're all human, aren't we? All right, so the next thing is then just what's the number? So I'm going to get -212,267. Yeah, I think I said that right. And usually we don't want to keep it in that, so we would have it as -212, and then with significant figures and in kilojoules. So I'm going to convert it to that. And so I get a spontaneous process, and my delta G is negative, just as I thought. Now, you could possibly take this one step further. Normally you don't have to, but knowing this fact is helpful. A larger E cell makes delta G larger. And again, we want an E cell that's positive too, okay? And what that means, and more importantly, is if you know that delta G relates to work, so you take a negative, it's called work max, or maximum work, and the negative sign will help get rid of the negative sign if delta G is negative because it's spontaneous. So what that means is the maximum work that you can get from something relates to the delta G, which relates to, back to, the cell potential. And again, make sure you catch that little mistake right there. All right, it's right now though. So there we go. We did our little calculation with our delta G, and we learned hopefully what some of these different things that are in this equation is. And we also modeled what it's like to be running continuously and starting to leave the standard conditions of no longer being at 1 molar, which leads me right into our next video, video number 4, which I hope you watch. All right, good luck, chemists.